Want to just take a quick look at graphs of solutions of these second order linear homogeneous differential equations with constant coefficients. When we had two real solutions, we had graphs that look like this right here. Maybe kind of hyperbolic cosine or hyperbolic sine type things. You're adding a couple exponential functions together. Right? When we had complex solutions to our quadratic equation there, then we ended up with solutions that looked like this or like that. That is a sum of sines and cosines that's then multiplied by an exponential function. So this is damped motion here. Damped harmonic motion is what it's called. Or exponentially growing harmonic motion. The thing to notice here is the exponentials are playing the role of the amplitude. And that the sine and cosine create a period. I mean, it's not really a period. It doesn't repeat itself, but it keeps going up and down at the same frequency. The amplitude is different each time. One of the things I notice when I draw my own graphs is that I have a tendency to, as the amplitude gets smaller, I make the period smaller, when it should actually stay the same, that the distance between these 2 points should be the distance between those 2 points, or those 2 points, and so on. Lastly, we had a situation where our quadratic equation had only a single real solution. And that's really the transition between these two situations. If you think about a graph of a parabola that intersects, let's say it's opening upwards, and it intersects the x-axis at two places. Now slide that graph upwards, and those two intersection points slide closer together till the time they get to a single point of intersection, and then you move it up even higher, and the graph, the parabola doesn't hit the x-axis at all, and you get complex solutions. So that transition between two real solutions and no real solutions is the one real solution. And the graphs are kind of in transition as well. These two graphs over here are a type of graph you'd see with t times an exponential function. So this one up here could be t times e to the minus t or something like that. That it goes through the origin because when t is 0, the factor of t is 0, and so you get that. But then where the linear function wants you to keep growing, the exponential function is trying to kill you off, and it brings it back down again. Essentially, this to me looks like one bump of this. It's not just a decaying, let's say an upside down decaying exponential here. It started to try to vibrate, it started to do this up and down thing, but then it didn't do it. It didn't have enough sine and cosine to it to keep it going up and down. It just came down and petered out like an exponential does. This would be the same thing upside down, maybe minus t times e to the minus t. If you had an exponential with a positive exponent, you just turn this graph around and it would go, up and then down, whatever. Essentially one bump of this infinitely many bumps. Okay. So the graph is kind of in transition, just as the solutions to the quadratic equation are in transition between the real solutions and the complex solutions.